Welcome to this video about ENiX natural language processing. The concepts in this video will refer to concepts laid out in the first video. So you may want to watch ENiX machine awareness videos 1 and 2 to supplement the ideas in this video. However, if you're just interested in natural language processing on its own, that's okay too. As an introduction to this video, in this first section we're going to talk about vocabulary, which is the basis of spoken English language. The first thing we need for communication is a place to store all of our configuration and memories of information, data and language. Databases make ideal places to do this. It's best really to have a very flexible, easy to use, feature-rich, fast and schemaless database to implement these ideas. When we come across language, we store the words even if we don't know what the words mean. Collecting a vocabulary is an important first step because words are an atomic component of language. We want to make this really easy so that systems can identify words passively, as adding words to a vocabulary one by one would be tediously time-consuming, and batch loading in a dictionary would add many words that we don't need. Now, through normal natural language processing, as well as words we want to acquire, we also collect slang, colloquialism and spelling mistakes. These are much less useful to us than a correctly spelt formal English vocabulary that is at the core of our language. They also take up storage space and slow down searches within the database. Also, keeping track of the meanings of all the derivative words and spelling mistakes requires complex processing, so it makes sense to keep only the words we use frequently. There's just over 1 million words in the English language. About 250,000 words in English are obsolete or archaic. Most people communicate daily with less than 200,000 words. So separating the words we want to keep isn't as straightforward as seeing if they're in a dictionary and deleting the others, as English vocabulary is constantly changing. Also, some spelling mistakes are common, and actually they are so common that it's beneficial to record them, even though they're incorrect. Examples are probably for probably, te for the, etc. So how can we sort out the words we need? How can we identify mistakes and delete them, but keep mistakes that are useful and regularly occurring slang? One of the ways we can weed out the words that we don't use is by statistical analysis. So we can assign a value of 1 to each word's probability. Then every night we can multiply the probability by an adjustable geometric ratio between 0 and 1, say 0.9, so that the word's probability, if unused, will have a probability half-life. And of course, when we see words regularly, we reset the probability back to 1 again. We can think of this nighttime processing of concepts as part of AI sleep cycle. We simulate forgetting by deleting words that have a probability that drop below a configurable probability threshold, between 0 and 1, say 0.05. This means that words that haven't been used by ENiX in a certain period of time will be forgotten, and ENiX's vocabulary adapts to changes in contemporary English usage and uses vocabularies. Over time, this filtration process will result in an expert system database with only useful words in them. Something we are particularly interested in language is the meaning of a word and the syntax of how the word is used. Words themselves are no different in many ways than numbers or mathematical constants. They are just symbols with no intrinsic meanings themselves necessarily, and we define the meanings of words relative to the meanings of other words. So really, the meaning of a given word is merely the relationship that that word has with other words. One thing that really helps us with understanding the meanings is being able to categorize words into grammatical articles with different function and properties within the sentence. Fortunately, English language has provided us with the names of the types of the words already. For example, nouns are objects, verbs are actions, adjectives describe objects, Adverbs describe actions, proper nouns are names. Conjunctions help us to structure lists of objects. Definite and indefinite articles help us to distinguish proper nouns from other nouns. Pronouns are concise substitutions for nouns so that sentences are easier and less repetitious. There are probably other articles of English that I've neglected here, but these are the most important ones. And of course, punctuation is also important, as this imparts a context to the use of the words, and as we know, the meaning of words is very dependent on context. For example, we know that we can put words a and the before nouns, but not proper nouns. We also know that if the sentence ends in a question mark, then the sentence is a question. The set of rules for permissible and unpermissible formats of context within a given language is called grammar. Once we understand these rules, we can construct and deconstruct sentences, and in the next section of this video, I will explain how these rules can be learnt by artificial intelligence. Okay, so in the last section we saw how we can create a vocabulary passively with minimal user involvement. And we saw that sentence structures, or grammar, dictates the layout of words within sentences. In this section, we're going to look at different sentence constructions and how they can be identified. These sentence constructions are called sentence moods. To talk about this, we need to introduce some very simple graph theory. No, a graph is not a plot of data in this context. Instead, it's a topological diagram of how different objects are connected. A graph in mathematics looks like this. Now there are special types of graphs that allow objects to be connected in one direction or both directions. We mark the direction of connectivity by an arrow like this. Objects that can be connected in both directions are connected by an arrow pointing both ways. Graphs with this type of ordering are called directed graphs. To apply directed graphs to grammar, we need to have objects that need to be related. Relating the words themselves would be difficult because the large number of them would mean that these graphs become very large and unwieldy, making calculation difficult or even impossible. It also means that it's very difficult and time-consuming to train the system because of the number of sentences involved in constructing the graphs. We can get around this problem by considering the types of words we use, namely the grammatical articles. So if we have a sentence like, "The cat sat on a mat," we can break this sentence down into grammatical types: start sentence, definite article, noun, verb, preposition, definite article, noun, full stop, and end sentence. So if we wanted to create a graph of this sentence, the directed graph would look like this. We have start sentence pointing to the definite article, the definite article pointing to the noun pointing to the verb pointing to the preposition pointing to the definite article pointing to the noun pointing to the full stop, and the full stop pointing to the end sentence. There are several different types of sentence moods. Yes and no questions. What we call WH questions, that's why, who, how, when, etc. Indicative sentences. These are informational sentences that provide data. For example, light has many meanings. Imperative sentences. These are instructional sentences that provide orders, like go home. There are also composite sentences. And we can construct these graphs by providing lists of grammatically correct sentences with words that ENiX has seen before. It doesn't take many sentences actually, we just need less sentences than the total number of valid word pairings of types of words in each graph. With just 50 or so well-chosen sentence examples, it is possible to construct an accurate graph that defines a sentence mood. It turns out that these different sentence moods have different graph layouts. These graph layouts look something like this. Note that these graphs are based on a small amount of training, so there may be some additions required to make them absolutely perfect. So we have a graph for yes or no questions, for WH questions, indicative and imperative sentence moods. If we have a given sentence, we can work out which of these it belongs to by creating a graph of the sentence and checking that it fits within our directed graph model of the sentence mood. If the sentence fits inside it, then the sentence belongs to that mood. For example, going back to our cat sat on a mat graph, we can check to see if it fits into these two sentence graphs as follows. Reading the graph from start sentence to end sentence, we trace this path through the directed graph, and if the directed graph doesn't have a link to that part of the example sentence, then we know that the sentence does not belong to that mood. Whereas, if all the links needed in the correct directions exist, then the sentence belongs to that mood. So why have we done this? Well, to have any hope of understanding what sentences mean, we need to break the sentences up into subject, predicate nouns and predicate verbs. And it's easy to do this using a collection of templates, and what a template allows us to do is to collect the words into subject and predicate groups. We represent the templates using the following symbols: S, which is the subject, PV, which is the predicate verb block, PN, which is the predicate noun block. The template symbols S and PN will collect nouns, proper nouns, definite articles, indefinite articles, adjectives and conjunctions, etc. Whereas the template symbol PV will only collect things related to the verb, such as the verb, any adverbs, etc. So for example, for the cat sat on a mat, we can use the sentence template S, PV, PN. This is how it works. The cat goes into S, sat on goes into PV, the mat goes into PN. And that gives us the sentence subject as the cat, the verb part as sat on, and the predicate nouns as the mat. Now we may need several templates sometimes. For example, for imperative sentence mood, we need the templates PV, PN, as well as PV, S, PV, PN. And we use whichever template works best. So in a nutshell, this is how we split up subject and predicate. In the next section, we will talk about more language concepts that aren't as important as the concepts in this section, but are necessary to provide a user with an easy experience of communicating with AI. In the last section, we looked at how we can identify sentence moods and use this identification to select templates so that we can deconstruct the sentence into subject and predicate components. In this section, we will look at how to construct sentences, as well as ways that we can help disambiguate meanings in conversation by expressing the sentences in a basic, standardized form so that AI has the flexibility to cope with information expressed in different wordings. Let's start by having a look at how we can construct sentences. Now I know that there's been a lot of research done in this area already, using things like hidden Markov models and Bayesian probabilities to construct sentences. I have taken a different approach which does not use Bayesian probabilities. Instead, what we do is we have a list of words that are jumbled up and we want to arrange them into grammatically correct sentences. Starting with the list of words usually, mice, cats, chase, we start by using a combination generator on this list of words to get the following list of possible sentences, some of which will be correct and some of which will not be. Now there are 24 of these combinations because we have 4 words, and these can be arranged in 4 factorial ways, or 4 times 3 times 2 times 1. If they were repeated words, we would divide by the number of repetitions factorial. So our formula for the number of combinations would be the number of words factorial divided by the product of the factorials of number of duplications of each element. Hopefully, we know what kind of sentence we are constructing. whether it's a WH question, yes-no question, indicative or imperative sentence. What we do next is, for each of these word combinations, is pass it through the directed graph of the sentence mood we hope to express it as. If the sigil of the combination fits in the directed graph, then it is syntactically correct sentence. From the combinations above, we get usually mice chase cats, usually cats chase mice, mice usually chase cats, cats usually chase mice. Note that mice chase cats usually and cats chase mice usually do not fit the directed graph filters because there is a comma missing before usually. Although these sentences are correct grammatically, they may not make sense semantically. Why would mice chase cats? We'll come back to this problem in later sections of this video. For now, we're just focusing on grammar. These directed graphs can help us to classify words that we've never seen before too. For example, if we use a word that is preceded by a definite or indefinite article, the sentence can only be grammatically correct if the word is a noun. So these graphs can help us to identify the categories of some new words without needing to be told. Another thing that can affect sentence construction significantly are sentence tenses. For indicative and WH question sentences, there are actually two different sentence voices called active and passive voice. For example, you could write, "People drive cars." This would be an active voice sentence, but you can also express the same information by writing it as, "Cars are driven by people," which is the same meaning but expressed as a passive voice sentence. Being able to determine if the sentence uses active or passive voice is important because if the voice is passive, then the subject and the predicate nouns are swapped over, and we need to take this into account when we calculate the subject and predicate of the sentence. Passive sentences are identified by using a past participle verb and a passive verb form. Additionally, the sentence will also use the word by to indicate that the clause that follows after is the subject. If the sentence contains only a passive verb form but does not contain a word by, then it's in actual fact an active voice sentence. For example, the cat was sat on a mat. This is active voice even though the verb matches a passive verb form because there is no by. A list of passive verb forms are listed here. We also have active verb forms too. Note that there is some overlap between active and passive verb forms. Some verb tenses appear in both active and passive forms, and they are ambiguous. This is why we need to include the word by to disambiguate which sentences are passive voice. Now there is little difference between the sentences. The cat was sat on a mat, the cat sat on a mat, the cat has been sitting on a mat, and the cat would have been sitting on a mat. The only difference is the tense. If we consider the tenses in this much detail in AI, then we may have trouble finding the exact sentence we need in the database when asking a question of a different form but of the same tense. For this reason, what we do is classify the predicate-verb component into past, present and future tense, and we keep a present tense simple verb. Additionally, we take any adverbs, sort them out alphabetically, and then add them to the end of the verb. So if we had the sentence, "The cat would have been quietly sitting on the mat," we internally represent the verb as sitting past quietly, and this makes it easier for us to look up related verbs. The sorting of the adverbs also helps us to find the same verb when the adverbs are stated in a different order by the user. As a final part to this section, it wouldn't be right for me to not mention something called the Porter-Stemming algorithm. Although I have little use for it in my research, it is a very useful algorithm if you're working with AI, so I should briefly explain what it is. The Porter-Stemming algorithm is a way to take verbs and some nouns, remove the suffix, leaving a base word. Again, this is potentially a very useful technique for disambiguation. For further information on this, please have a look at the Wikipedia article on it, because it's quite well explained. That concludes this section on sentence construction and tenses. In the next section we will cover how we can efficiently store and represent language more generically. In the last section we looked at how sentence moods are broken down into active and passive voice, and we looked at tenses and how we can represent them in a generic way. In this section we're going to cover how to express noun clauses in a succinct and storage-efficient manner. Additionally, we're going to look at how we can represent meanings generically and in a way that allows us to easily locate data. As we did with the predicate verbs, when we separate subjects and predicate nouns, we express these clauses in the standard form. Typically, we disregard the definite and indefinite articles, and we place the singular noun first, followed by any adjectives sorted alphabetically. So if we have the clause, the tall green trees, we would express this internally as tree, green, tall. Now, internally, storing all of these words would be wasteful, so we store contexts for the clauses. This gives us the flexibility of having the entire context, but with the advantage of a much shorter form of representation. The context addressable memory location can be dereferenced back into the context address. In ENiX, the direct reference to this address is represented by a CS number, where the letters CS are suffixed by a denary number. How do we represent addresses as symbols? We start off with tree, green, tall. We represent tree as just tree. Tree green we represent as CS1. We represent tree green tall as CS1 tall and represent CS1 tall as CS2. Note that each step stores a pairing of words and/or context address symbols. We store the first part of the context in a qualifier column, and we store the second part of the context in a value column. So when we come to dereference the symbol CS2, all we need to do is find the record called CS2, then we get the context CS1 tall. Then we dereference CS1 by finding the record called CS1, and we dereference that, which gives us tree green. We add this to our previous suffix of tall to give us tree green tall, which is our original context for the reference CS2. Now if we have two clauses starting with tree, say tree green short, then we can recycle CS1, which represents tree green, and then we can add short to produce CS3. Note that we do not have to store tree and green again, so we are representing two word pairings with just one symbol, CS1. The second time we have a shared context in a clause. Now, what all this means is that we can do fuzzy searching on contexts. For example, if the information we're looking for is tree, brown, tall, and we search for tree or tree short, we can easily find the shared context from the information in the database. If we search for tree, we get this. If we search for tree brown, we get this. For fuzzy searches, when we search within contexts, if we search for tree short, we get this. If we search for tree tall, we get this. This allows us to search for related contexts too, by seeing if there are similarities between the context addresses which give us a shared context. In particular, we are interested in the similarities between the noun part of the context. Additionally, we can compare related concepts, and it allows us to explain, by the adjective differences, in what way the clauses differ in meaning. Furthermore, it allows us to classify noun clauses by adjectives and search for them. So that concludes this section on context addressable memory and how we can disambiguate noun clauses. From the next section onwards, we leave the fundamentals of grammar and start looking at the actual processing of language in meaning, semantics, and semiotics. In the last section, we discussed context-addressable memory and how this can be used to store information and locate it in an efficient manner. In this section, we'll look at how to store and retrieve sentences so that we can answer questions in English, and we'll have a look at another way to represent the meaning in sentences. We've already seen how we can represent chains of words as context-addressable memory locations. What we can do is we can store sentences as subject and predicate noun clauses under a record named the predicate verb. So if we have the sentence, "The sky is blue," then we can represent that as the sky, which is the cause, is, which is the verb, and blue, which is the predicate noun clause. So if the sky is CS6, is CS7, blue is CS8, then we can store the qualifier value pairing of CS6, CS8 respectively under the verb CS7. When we come to ask a yes or no question, we can ask, "Is the sky blue?" Then we can separate out the sentence into subject and predicate and look at whether CS6 and CS8 occur under the record CS7. If we ask a WH question, "What is the sky?" then we again separate the subject and the predicate, and we find the predicate clause by looking up the subject, which is CS6, under the verb, which is CS7, and paired off against the subject is the predicate clause, CS8. We read this clause out of the record and dereference it back to an address, which is blue. When we construct sentences, as we saw in previous sections, we may get grammatically correct sentences, but not semantically correct ones. So what we can do is check to see which sentences match the meaning of the sentence stored in the database. In practice, however, we don't do this. Instead, we already have the information we need in almost the form that we need it in. For the verbs, we conjugate the tenses with the appropriate active or passive form, drop the name of the tense and move the adverbs before the verbs. For the nouns, we add in the definite or indefinite articles and move the adjectives before the nouns. We then attempt to construct a simple sentence in active voice. If we wanted to construct it in a passive voice, then we change the verb form to a passive verb form of the correct tense, insert by, and then swap the subject and predicate noun clauses around. Internally, we can also have routines which change the sentence mood, or change the voice, or the tenses of the sentences. So this allows us to create relationship associations, and we can create multiple associations, and there's no reason why we can't chain these associations together using associative properties. The associative law in mathematics is either of two laws relating to number operations of addition and multiplication. Stated symbolically, A plus B and C equals A and B plus C, and A times B and C equals A and B times C. That is, the terms or factors may be associated in any way desired. And what this allows us to do is to daisy chain associations together. So as the system picks up more information, it can associate exponentially more information. I call this automatic learning propagation because new data is becoming associated automatically through association. Okay, so in the last section we discussed storage and retrieval of information and how things can be associated exponentially in unsupervised learning with no active intervention at all, once the system has been trained. In this short section, we're going to move on to something totally different. We're going to talk about how we can track what is being discussed in topic tracking. When we discuss things, we usually have like a train of thought. This train of thought produces a series of ideas that are related in topic. Sometimes, however, when we're thinking or discussing things, an idea will change a topic of conversation into something completely unrelated to the previous chain of thoughts. It is crucial that natural language processing systems can collate related concepts together in groups and detect when the conversation is changed to an unrelated concept. We call this topic tracking, and the way we do it is actually not all that difficult. What we do is we start by collecting a sentence and adding it to a new group. Now, when a new sentence comes into processing, it is deconstructed into subject and predicate, and we compare if nouns or verbs are related to any of the subject or predicates in any of the sentences of the group. If they are, then we add this new sentence to the group of related sentences, and our group grows a little in size. Now, as we know from automatic learning propagation, as the group of related items grow, so does our probability of finding a new related item to our topic through associativity. However, when a new sentence comes in that is unrelated to the previous sentences in nouns or verbs, etc., then we don't add it. Instead, what we do is we empty out the group and we add this new sentence into a fresh group all alone, and the processing starts again. So how does it know what is related? For this, we need to be able to detect whether the meanings are similar. So one way we can do this is obviously to look at whether the nouns and the verbs, etc. are the same. If they are, then clearly they are related. If the nouns are associated as being equivalent in meaning to other nouns, then again they're related. If verbs are a different tense or conjugation, then again they're related. We can also look at loosely linked meanings by seeing whether or not the nouns have no more than one degree of separation from being defined in terms of a noun in the topic group. If the degrees of separation are higher than that, then we consider the sentence unrelated to the topic group and do not include it. We should store topics in a database so that we can refer to them again in the future. Topic tracking gives artificial intelligence a conversational context, which is very important because otherwise it would just perceive information learned years ago as being equally relevant to information learned today, and that's just neither realistic nor practical. Topic tracking also means that we can use pronouns, because we can take subject and predicate nouns and substitute them into pronouns. Then, when we use pronouns in the future, they can be expanded into the nouns that the pronouns represent. Before we can substitute pronouns, though, we need to know a bit about the nouns. In particular, we need to know if they are male, female, or neutral gender, so we can use he, she, or it, respectively. If they are plural, then we use they or them. When we add information to the topic group, we check these nouns and we substitute these nouns into the pronouns. Then, where we see pronouns being used, we expand the pronouns into the nouns that they represent. In the previous sections, we talked a lot about language features, but so far we haven't said anything at all about how to deal with malfunctions. If the system goes wrong or doesn't behave in a way that we expected, how can we fix it? In this section we will cover the safety features needed for an AI system capable of communication. There needs to be a mechanism for directly controlling an AI system that's outside of the realms of normal language. One way that works is to implement a programming language which has commands that are prefixed by a colon. These commands are used to train the system to speak English and cannot be overwritten. Learnt words, however, can. The commands can be associated with English words. This means that if you attempt to fix an issue with the system and the language is not correctly set up, and the system has reprogrammed English words to represent commands, then it can be very difficult to undo any faults that arise. So in the event of a fault, we can undo and bypass the training directly by using commands. There needs to be several commands. One is to wipe the database in an emergency situation. Another is to undo the previous command. Also, there should be save and restore states of ENiX called personality profiles. So let's talk a bit about the commands. When commands are substituted into words, we can implement a system that recursively looks up a word's commands. The problem is that when we have such a system, we can have contradictions and recursive definitions. For example, we can say that true is false and false is true. We can also have cyclic definitions such as new is news not ENiX. If we have a system that recursively looks up these definitions, then we can actually get into situations where the system is recursively substituting forever. To stop this from happening, we need a paradox handler, and to implement this we need to keep a record of the symbols we've evaluated. When a substitution evaluates to a symbol we've visited, we can stop the substitution as soon as we detect a paradox or cyclic definition, and revert the substitutions back to their original expressions. Now, if the system detects revisiting any commands in the expression the user provides to it, it should cease natural language interpretation and pass the expression through an internal command interpreter. Now, sometimes a natural language processing command needs to be associated with the type of sentence. We associate commands to verbs, and we do this without going through substitution through a verb lookup table. It works by having a record in a database with verbs referencing commands. When a sentence occurs that contains the verb in a lookup table, the entire sentence in its entirety is interpreted through the command or commands that the verb references. This is particularly useful for interpreting indicative and imperative moods, because this allows the system to be instructed using English. For example, go outside or calculate the solution. The words go and calculated can be attributed to actual internal functions that process the sentences go outside and calculate the solution, respectively. In the last section, we looked briefly at safety features and how to control the system when it malfunctions. We also looked at how verb lookup tables can be used to control behavior based on the verbs used in sentences. In this section, we're going to look at an important area of natural language processing, conditional sentence processing. It's important because it allows us to relate sentences together using logic and, more importantly, using neural networks, which allows us for the first time to have awareness of the quality of the decision-making process in language. The first thing we need to do is be able to determine if a sentence is a conditional sentence or a normal one. Conditional sentences contain words such as if, when, because, then, where. So we need to store these words in a database record so that we can detect conditional sentences. If, when, because, and where mean that the following sentence is the cause of the conditional, whereas words like then and so mean that the sentence following is an effect sentence. Next, we separate conditional sentences up into cause and effect sentences. Now we need to keep a record of what conditional sentences the system has seen. If we do not, then the observations will be indifferentiable from conclusions, and it will mean that if an observation is found to be incorrect and needs to be altered, then the conclusions will pollute the observations and prevent different conclusions from being formed from the new observations. A possible alternative way around this would be to force the user of AI to re-enter all the observations, but this would be tedious. So when we start with a conditional sentence like, if the mouse sat on a mat, and the cat and the dog sat on a mat, then a dog sat on a mat, we break it down into the cause sentence, the mouse sat on a mat, and the cat and the dog sat on a mat, and the effect sentence, the dog sat on a mat. After that, we separate the causes and effects into multiple conjoined sentences by looking at the Oxford commas. So that's commas followed by conjunctions. So for example, the cause sentence, the mouse sat on a mat and the cat and the dog sat on a mat, this breaks down into two conjoined sentences. The mouse sat on a mat, the cat and the dog sat on a mat. Finally, we separate the conjoined sentences into simple sentences. So the cat and the dog sat on a mat becomes the cat sat on a mat and the dog sat on a mat. We store the cause and effect sentence pairings in a record, we store the relationship as a non-negated CS effect variable, and then we store the lexicographically sorted list of causes next to a yes value and the value of the attribute adjacent to the cause sentence symbols. If the sentences are negated, things get a bit more interesting. If we had the conditional sentence, if the dog sat on the mat, then the cat was not sat on the mat, then we disregard the negation for now, and we still store the cause sentences under the non-negated effect sentence symbol. Instead of marking the value as yes, we mark it as a no to represent the causes do not cause this effect. Now, when we have negated causes, we can exclude them completely from the list of causes that causes an effect. If there are no causes, we can store nothing instead of the sentence symbols. Note that we cannot do this with effect sentences in conditionals because otherwise we have no way to relate the causality of the cause to the effect. We have to know whether a cause produces or prohibits an effect. The layout of this storage is from multiple causes to a single effect. Taking an example where we have multiple effects, if the woman opens the door, then a bird and a cat escapes. In this scenario, we can divide the sentence into two separate conditional sentences. If the woman opens the door, then a bird escapes, and if the woman opens the door, then a cat escapes. So, even though we only store many-to-one relationships, we can duplicate the causes across many outcomes to completely represent the problem. Please note also that we cannot determine an outcome from a cause of nothing unless it is specifically stated. It is an indeterminable problem. So this is how we store conditional sentence information so we can refer to it and correct it later. So how do we connect this information to a neural network? We've already covered this in the machine awareness video, but let's cover it again here. Each simple cause and effect sentence in a conditional sentence has a context address. So, let's suppose we have saved a problem that looks like this in memory. Then we can assign exponents of 2 as follows: CS1 as 1, CS2 as 2, CS3 as 4. Although 0 is not an exponent of 2, we assign nothing as 0 also. We can write nothing as 0, CS1 as 1, CS2 as 2, CS1 and CS2 as 1 plus 2 equals 3, CS3 as 4, CS1 and CS3 as 1 plus 4 equals 5, CS1 and CS2 and CS3 as 1 plus 2 plus 4 equals 7, CS2 and CS3 as 2 plus 4 equals 6. We can represent yes as 1 and no as 0. If we encode the yes and no values at encoded positions, we see the sequence 0, 1, 0, 1, 1, 1, 1, 1. As we know from the machine awareness video, we can translate the problems into a number sequence called multiplexing. Then teach a neural network to learn and understand this number sequence, and it can provide a degree of awareness about whether the number sequence is understood. Once a neural network is learned, we can ask it questions. If we want to know an effect from a cause, CS1 and CS2, then we can calculate the position of the sequence, which is 1 plus 2 equals 3, and we can execute the neural network at position 3, and this will give us the value of 1. Remembering that our sequence starts at position 0. So this gives us yes, so CS4 is caused by CS1 and CS2. If we wanted to know what caused CS4, we could work out the complete series across all the values and list all the positions in which these values are 1. That's positions 1, 3, 4, 5, 6 and 7. This corresponds to causes CS1, CS1 and CS2, CS3, CS1 and CS3, CS1 and CS2 and CS3, CS2 and CS3. If we wanted to know what did not cause CS4, we would list all the positions which are no. That's 0 and 2. These correspond to nothing and CS2. Now in this particular example, we could have just looked up the information from the observation cache. We didn't need to have a neural network involved at all. But if we change the example slightly and cease to provide CS1, CS2 and CS3 as an example, then our multiplex sequence would be 0, 1, 0, 1, 1, 1, 1, question mark. As you can see, the last term in the sequence is unknown. If we wanted to calculate it, all we need to do is execute the neural network at position 8, and this will calculate our value of 1, i.e. yes. We could also detect weird anomalies. If our multiplex sequence was 0, 1, 0, 1, 1, 0, 1, 1, then we could use the neural network to detect that the third 0 is probably a mistake, and we could get the awareness metrics from the neural to highlight and take the appropriate action. If you would like to find out more about the neural networks I use in my research, I suggest you look at my previous video, Machine Awareness. This gives a very detailed explanation of these neural networks, describes how they work, and explains why they are aware and what they're capable of. In the last section, we covered how neural networks can be connected to natural language through conditional sentences so that we can calculate causes and effects of situations. In this section, we'll cover how to use this in reasoning so that we can solve problems and plan actions. There are two basic forms of reasoning. The first is reductive reasoning. This is essentially breaking down a situation into its causal factors. There's a long history of philosophers who have worked on reductionism, notably René Descartes, who believed that animals can be represented as a construction of automata. In De Domine of 1662, he drew this drawing of a duck. A lot of the research I've done follows reductionism and can be used to define ineffable things such as awareness. So how can artificial intelligence do this? Well, we can already determine causes of events if we have some empirical evidence of what causes produce an effect. If we collect all these observations, we can learn a neural network to model a causality. But this will only take us to the direct causes of the event. We need to be able to go back further, as far back as we need to. And that actually isn't very difficult for us to do. We use conditional sentences and we work out the direct causes. Then we work out the causes of those causes, and so on. We can keep working backwards as far as we like until we get as many causes as we need. At each calculation of a cause, we involve a neural network computation, and this will evaluate any cause combinations that are likely to produce the effect. We just need to be a little careful, because many different causes can create each singular effect. So the further back we go, the more the tree of dependencies grows outwards. We need to keep branches separate and be careful with displaying our results so that we don't mix causes from separate branches. The other type of reasoning is deductive reasoning, which is where we know the initial state of the problem and we want to work out what the future consequences of these causes are. These are what-if scenarios. Again, we can recycle the work that we did in conditional sentence processing and we daisy-chain the conditional sentence processing together. As with reductive reasoning, we need at each step of the reasoning some real-world examples or observations to provide causal examples. The neural network can fill in the gaps missing from these examples and produce a holistic model that models the known examples perfectly, and hopefully models the unknown examples accurately also. If we use the neural network defined in my previous video, machine awareness, this neural network will provide metrics for whether the data makes sense and the model is good. Unlike with reductive reasoning, we do not need to keep branches separate because multiple causes narrow down into one effect. It's a many-to-one relationship. So if the causes result in multiple effects, then we need to add the effects and use them as causes for the next step. Note that for practicalities, limiting the number of steps in both reductive and deductive reasoning is advisable, because sometimes you can get cycles of causes and effects, and too many steps can actually be superfluous. The mechanism for questioning yes or no and WH questions is the same as for conditionals. The only difference is that with yes or no questions, when we are determining if something can be caused by a scenario, we make sure that all the effects are in the evaluated outcome. When we are determining a cause, then we have to exactly match the evaluated causes of an effect. If they do, and only if they do, they are a yes. Otherwise they're a no. We can actually extend the reductive and deductive reasoning to calculate how to solve problems, physically move robots to get to places, and perform complex sequences of actions. Extending the reasoning to perform actions rather than process information should be trivial. One last thing in this section that I should mention is that using underfit neural networks would produce bad results for linguistic reasoning. This is because the amount of data required to form a model would be a lot, and unfortunately for these types of problems the data available tends to be very limited. Additionally, underfit neurals like backpropagation and feed-forward don't match data points exactly and have different metrics of awareness. In the last section, we saw how we can use neural networks as a reasoning tool to convert observations into actual models used to predict future and past events. In this video, we'll go through some advanced applications of language. Something we haven't mentioned at all in this video so far are personality profiles. We can have different personalities stored in AI, and we can load and save them one at a time. Each personality has a different knowledge base, so may have a slightly different understanding of language, vocabulary, how to solve problems, training, and of course memory. Information should be transferable between personality profiles. Unfortunately, this requires dependency checking because as well as moving the concepts themselves, all the database records that the concepts are based on also need to be transferred. Implementing translation should be possible too in theory. Once we translate the verb, adverbs, nouns and adjectives, we can add any missing articles. For example, we could use the definite articles li, la, les if it's French, and we can use directed graphs of the French language. We should be able to form syntactically correct sentences in another language. For languages that are declension-based and fairly regular, we can adapt the Porter-Stemming algorithm to make sure everything is in the correct declension. We need to be careful, however, because words can have multiple meanings, and we need to disambiguate the meanings by context. Luckily, articles have similar functions in other languages other than English. We can also sanity check that our meaning is correct by asking questions in French or whatever language we're translating into, and then we can translate the French verbs and nouns into English and internally ask the same questions in English. This will verify if the meaning of the sentence that has been translated is valid. There is no foreseeable reason why other languages, like French, cannot use similar methods to reduce sentences into subject and predicate forms. The last thing I want to talk about in this section is the concept of sleep. In the first section of this video about vocabulary, I mentioned that to keep the vocabulary accurate and up to date, and identify and remove errors, we need to regularly check if each concept is used. And if it isn't, we need to move the unused concepts closer to deletion so that the system can forget useless information. It makes sense for this process to occur every night when the AI is not likely to be used. Now there is another kind of processing that would be useful to do during this quiet period. During the day, the system is exposed to quite a lot of information. An example of this is vocabulary. Now the system may not be able to work out what all the words mean automatically at the time. For example, something may be said early in the day or on a previous day that uses vocabulary that is unknown. We can store these sentences into a conversation buffer. Then, when more information later occurs which reveals the meaning of further words, there may be enough information to find out what the earlier words meant. To do this, what we can do is we can process all the sentences in the conversation buffer, and if any new words are learned, we can run through the conversation buffer again and again until we find as many words' meanings as we can. When we do a complete sweep of the conversation buffer and there are no new words learned, then we can stop going through the conversation buffer. Of course, once a sentence in a conversation buffer is completely understood, then we can remove it from the conversation buffer so that it isn't passed in future sleep cycles. We may also want to add additional processing to limit the size of this conversation buffer so it's not unwieldy to process it all. We can also envision situations where we have conversations about separate topics during a day, but in retrospect may actually be related by deductive and reductive reasoning. During this time of sleep, we can go through data collected and form neural network models so that we can access them faster during the day. We can model scenarios and test to see if the information we have makes sense. Just as animals do during sleep, we need to paralyze the system when modeling the data so that it does not actually act out any actions and cause any harm. This involves preventing any actions from occurring that are not directly related to alert processing of information. We also need to protect the data that we accrue from modification by erroneous data. Potentially, it's extremely computationally intensive to create neural network models for things. We don't want these neural networks being overwritten by incorrect information. Because of this, it's good to verify any information that differs from the neural network with skepticism. We can do this by doing an odd man out calculation with the new data as well as the existing examples. If the new data is detected as an odd man out, we should reject it until there is proof that the system's formed model is actually incorrect. Of course, we can always use the safety features of the system to override any erroneous behavior. So these are some of the more advanced concepts that language provide us, and things we could implement in the future. Some of these ideas have been partially implemented before, but other things such as language translation I cannot take forward because my foreign language skills are not good enough. So that is it for this video. I hope you've enjoyed watching it, and I hope to cover more of my research soon.